Hey there. So today we are going to be looking at three logical puzzles, and the first of them is the poisoned wine problem. And this problem has been covered by some sources on the internet before, so I'm not the first one, but I'm not going to be discussing the solution to this problem today. I'm going to be discussing some different aspect which will possibly lead us to a master key to solve all such puzzles. So obviously there is no single solution to all such puzzles, and if there was, I certainly wouldn't be the first one to find it, but I've noticed something, and I think that it can come in handy in all puzzles of this sort. So let's get started. What does this puzzle say? Well, there are 1000 barrels of wine, exactly one of which is poisoned, and you have 10 rats which can be fed the wine to check if it's poisoned or not. If they drink the poisoned wine, then they'll die, and otherwise they won't. And each rat can drink wine from as many barrels as you want, but they can drink only once. So the poison takes 1 hour to take effect, and the party starts in 1 hour. So you have to feed the rats the wine immediately right now, and then you have to wait till the party starts for the poison to take effect, and only then you will find out which rats die and which don't. So you can't feed the rats the wine once again. So you can't take the rats who don't die and then feed them the wine once again, because the party has already started. Now is the time you have to serve the wine. So you can only feed it once in the beginning, which is now, and then 1 hour later you'll see the effect, and you have to find out which wine was poisoned. And all the wine must be ready at the beginning of the party, so you can't check the first 100 barrels and then serve them, and then check the next 100 barrels and serve those, and so on. So all 1000 barrels should be ready in the beginning of the party. So your task is to find out which barrel of the wine is poisoned, and you have only 10 rats to do it. So can you do it? And you can pause the video over here if you want to solve it on your own, and or if this is the first time you are seeing this puzzle. And now the solution to this puzzle by Hey Mathists and Creative Math Solving over on Instagram is on your screen right now. Now the solution may seem a bit out of the blue, so now we are going to be taking a look at the intuition behind the solution, and that will lead us to what we were after. So what we'll do is we'll look at what we know and what we want to find. So that may not sound that useful, but what we know and what we want to find is the most important thing you can check in a puzzle. So what we know is which rats die and which rats live. So we can call that the state of the rats. So the state of the rats is basically the combination in which the rats die and live. And what we want to find is which barrel is poisoned. So we can call that the state of the wine. So what we'll do is we'll make two sets, I and O. So I is the input set, which is the state of the wine. So I is the set of all possible states of the wine, and O is the output, which is the set of all possible states of the rats. So what we can do is now we'll find some way to encode the state of the wine and the state of the rats. So the state of the wine is pretty easy. We can number all the barrels from 1 to 1000, and the state of the barrels or state of the wine is basically the number of the poisoned barrel. So if we know the number of the poisoned barrel, then we know the state of the barrels. And the state of the rats, well, we can number those from 1 to 10, and then for each rat we can write either D or L, dead, or D or A, dead or alive. So we have the rats 1 to ... till 10, and for each one we'll write dead or alive. So in this case 1 is dead and the rest of them are alive, let's say. So rather than using D and A, what we can do is we can use 1 and 0, and that will give us a binary number. And now you can see how we are building up to the solution. So basically what we are saying is that there are 2 to the power of 10 possible states in which the rats can be alive or dead, and each one will correspond to a unique binary number, a unique 10-digit binary number. So from all the way till 10 zeros to 9 zeros and 1 till 1 and then 9 zeros. So those are all the states in which the rats can be, and we know the state in which the rats are. We want to find the state of the wine. So now what we want to do is, we are given some output and we have to find the corresponding input. So what we'll do is, we'll draw the set O. Let's say these are the elements of O. I'll denote them with dots. And we have I with these elements. So we have, let's say, this output, we get this output, then we want to find which input does it correspond with. So let's say it corresponds with this input. So in this case, we know that if we get this output, then that means that this input must have happened, and that way we can determine the state of the wine. And likewise, if we get, let's say, this, then let's say it corresponds with this. So then we know that this was the state of the wine and this is our answer. So this way we want to link all of the outputs with some of the inputs. And the crucial thing is, every input must have exactly one output, and every output can have at most one input. So it can be that this particular output is not linked to any inputs. That's completely fine. But what we can't have is that this output is corresponding to two inputs, because if this is corresponding to two inputs, then we don't know which one happened. So if we get this output, then we have no clue what exactly happened over here, because we have two possible solutions. So we want a function from O to I, or rather we'll say the other way around, I to O, and this must be 1 1. So what this basically means is, every element of I must be linked to at exactly one element of O, and every element of O can be linked to at most one element of I. So pause the video if you like over here and ponder over this a bit. Now you may think that bringing in functions and sets and all in a simple puzzle which had nothing to do with mathematics seems kind of random and kind of overkill, but it is not. We are just looking at a logical sequence of reasoning, and we are only using sets and functions to formalize that reasoning and get our point across more clearly. And in fact, this tells us one more thing. So what if we had 9 rats and 1000 bottles of wine? So obviously, using the binary solution which you saw a while back, that can't be done, because we have 512, which is 2 to the 9 possible states for the rats, but we have 1000 possible states for the wine, so it can't be done. But can you show that it can't be done with any method? So what if I'm really smart and I come up with a new method to solve this question? Can that method also not be able to solve the 9 rats and 1000 barrels of wine case? Think about it for a while. The answer is no. And the proof is hidden right over here. We want to find a function from I to O which is 1 to 1. That means that the number of elements in O must be greater than or equal to the number of elements in I, because if that's not the case, then this can't be done. And if this can't be done, then we can't solve the problem, because this is the only possible way to solve the problem. You have to have a mapping from O to I which is 1 1. If it's not 1 1, then you can't solve the question, because then you'll have two possible inputs for a given output. That means you can't determine which input it was, and hence you weren't able to solve it. So it must be 1 1, and it must be from I to O, obviously. So this is the only possible way. We have to find some mapping. Without a mapping, the question can't be solved. No matter how smart you are, it's mathematically impossible. And now we'll analyze the second puzzle to look at this method in action. So the puzzle is, you have 10 chocolate making machines, one of them is defective. So all of these machines can make as many chocolates as you want, and exactly one of them is defective, and the one which is defective makes 2 gram chocolates, and all the other ones make 1 gram chocolates. So you have to find which machine is defective, and you have a weighing machine which you can use only once. So you can make as many chocolates as you want from each machine. You can put them in the weighing machine and you can see the weight, and that is all you have to answer the question which machine is faulty. So now, instead of revealing the solution, I'll go through this method of 3 steps with you and we'll see if we can end up at the solution. So what do we know? Well, we know the mass of the chocolate, and we also know, so what I'll do is I'll write it over here. So what we know is the mass or total mass of the chocolates, and we also know what the number of chocolates which we put in. So we also then know the number of chocolates which we put in from each machine. So let's give this a name. So since we have 10 machines, let's say we have A1, A2, A3 and so on till A10. These are the numbers of chocolates we put in from each machine. So A1 is the number of chocolates we put in from the first machine, second machine, third, 10th machine and so on. So this is what we know. What we want to find is defective machine. And we have to find a function. So, well, we need to write I and O in terms of sets, right? That's how the method worked. But no, that's not what you need to do. That was just a method of explaining. So what we'll do is we'll think about it without drawing any sets and all. So let's look at what the total mass will be in terms of all these numbers. So let's say machine number 1 is faulty, okay? So assumption one is faulty. So what that will do is the total mass will equal A1 plus A2 plus ... till A10 plus A1, right? Because from A1 we took from machine number 1 we took A1 chocolates which are each of mass 2, and from the rest of the machines we took A2, A3 so on till A10 chocolates which are each of mass 1. So this is the total mass, and you can already see how we can find that 1 is the faulty one, right? Because this is also equal to 2A1 plus A2 plus ... till A10. And what we also know is that if machine number I is faulty, then over here we'll have AI, and this sum is always constant no matter what the value of I is. So what we can do is we'll call this S, and obviously we know S because we chose the values of A1, A2 so on till A10 on our own. So the total mass is equal to S plus AI. So what we'll do is, since we know S, we can subtract off S, and that will give us AI. And since we know AI for all I, we can basically take an inverse of this. So using the value of AI, we'll find I, because we can choose the values of AI as we want. So what we'll do is we'll choose different values for all of these. Let's say this is 1, 2, ... till 10. So if machine number 1 is faulty, we'll have 1 extra gram. If machine number 2 is faulty, we'll have 2 extra grams. Machine number 10 is faulty, then we'll have 10 extra grams, and that way we have solved the question. So now you have looked at the solution to 2 puzzles in which you saw this method in action, and I'm claiming that this method is more powerful than you might think. It seems really simple, but it's really powerful, and that's the thing about most powerful methods in logic and mathematics in general. They tend to be rather simple to state, but they are really powerful. So now, to give you a challenge and see if you actually understood the method, here's a puzzle for you on your screen right now. And now the challenge for you is to figure out what the mathemagicians were doing behind the scenes. And the solution will be out on Friday over on my page. The link is in description. You can check it out over there. So follow me over there. The solution will be out soon. And thank you for watching.
Thank you for watching.